Okay, hi team, we're on to nuclear reactions. And nuclear reactions, we're going to start off with the real core basics to make sure we know where we stand. Okay, mass is lost in all our nuclear reactions, the ones that actually happen naturally, and this lost mass is called the mass defect. Okay, and the mass defect is the missing mass, or the mass that's lost in the reaction. Okay, the mass defect is entirely converted into energy, and we can calculate that energy using E equals mc squared, where m is the mass defect and c is the speed of light, which we will square. So it's handy to remember that 3 times 10 to the 8 becomes 9 times 10 to the power 16 when you square it. So, and what is that? How is this energy showing up? The energy is seen as the kinetic energy of the particles which fly away quickly from the nuclear fission or fusion. It's seen as the kinetic energy of the particles or as electromagnetic waves, ordinarily those waves being gamma rays. So it's seen as one of those two things. Now, I thought it'd be a good idea to whiz quickly through what kind of things we are going to see by way of nuclear reaction. So if we start off with perhaps the one that we don't see very often. Okay, fusion is thought to happen in the sun, and in my picture, fusion is small nucleus plus small nucleus goes to larger but still probably fairly small nucleus. So small, small. Now in terms of what this would look like as an equation, I could say, well, let's draw it out differently. My small nucleus could be, this is the 1 proton, 1 neutron. Now, 1 proton, anything with 1 proton is hydrogen. 1 proton with the neutron is the hydrogen isotope that we call deuterium. And of course here, I've got 2 protons. Now I've got 2 protons and 2 neutrons. And that's what we normally call helium. So here we've got the situation where I've got the deuterium isotope. A proton and a neutron means I've got a 2 here for the mass number, as the chemists call it. As we, in physics, I always used to call it the nucleon number, the number of particles in the nucleus, nucleon number. But if you're doing chemistry too, it's probably easy to remember it as mass number. And then, so I was brought up on proton number and nucleon number, but you might know those as mass and atomic. And obviously, this is the deuterium hydrogen isotope. So it's a hydrogen with 1 neutron and 1, and that's called deuterium. Hydrogen is the only element, or hydrogen has the only isotopes which have individual names. So normally isotopes are just named by how many neutrons they've got. So you could have, say, carbon 14. Carbon 14 is famous for dating. So deuterium and tritium. Whereas, say you were talking about carbon, you'd say, oh, I've got my normal carbon 12, but it's also possible to have a carbon 14 isotope, and this doesn't have a name. Its name is carbon 14. Okay, so, and it's the same with uranium. You might say, okay, uranium is famous for having its very highly fissile isotope of uranium-235, and its other isotope of uranium-238, which is the more common one, and also it has a 239 isotope, and I imagine there are other isotopes that are also short-lived, but none of these has a name, whereas hydrogen has these 2 isotopes, deuterium, which is this one, and tritium is the one that's 2 neutrons, and so tritium is, just for completeness, tritium is, so that's neutron, neutron, and proton. And tritium is the radioactive one that you get on watches and things like that. It's a much more radioactive hydrogen isotope. Okay, moving on. Let's look at different types of fission. Now, I made a slight mistake here, but here it would be a spontaneous fission. So spontaneous fission, okay, spontaneous just happens. Spontaneous doesn't need anything to get it started. It's a bit like a party where it just randomly happens. There's no invitation, there's just nothing going on. It's just a few people happen to be there and a bit of a party took off. It was spontaneous. So uranium, and we might have some beryllium, we might have some krypton, and these are neutrons, of which you might get 2 or you might get 3 in this slightly different setup. So, and what you've got to remember, that I should have said earlier, is that of course, if you add up the masses of all these things, they will have to have, so if you had this mass and this mass is now less than that mass. Because, and the missing mass is the defect. And the energy of the defect is shown in the fast movement of all these things. It's in the kinetic energy and possibly in gamma rays that were given off. Okay, here's my equation for the next one. So my next one, which perhaps not very helpful, my next one, so I could get rid of that one and say, okay, let's look at this one. It's also possible to just give off so I could go from thorium, which occurs in rocks, to radon, which occurs in the air, and I could just give off a alpha particle, 2 protons, 2 neutrons. So there's my alpha particle. And in doing this, I've got a very simple equation because I've got 234, 230, and so I've lost 4. And you'll notice I've gone from 90 to 88. I've lost 2 in the protons, lost 4 in the nucleons, because I've lost an alpha particle, which I could represent as a helium nucleus quite accurately. Okay, so that's my second one. So I had a big uranium, which gave off neutrons and split the atom into smaller atoms. Or you could just have a nucleus becomes a slightly smaller nucleus and gives off an ionizing radiation as a particle. Or it's possible that it could give off a particle and also a gamma ray. Sorry, I've got wrong there. The gamma is that one. Okay, that was an attempt at a wave going away from the nucleus, that one. That one's gone a little bit astray. But that was my gamma ray going away from the fission event. Okay, other types of fission. So, fission. Induced fission. Now, if you want something to happen, you induce an event. So, induced fission, okay, if you want someone to do something, you might give them an inducement. An inducement might be a good euphemism for a bribe. So, if I really wanted, anyway, let's just move on. I don't want to talk about any specific bribing events. So here we have a neutron. Okay, have I got names for this? No, we've got a neutron here. If this meets a uranium-235, now I think from memory, there's only uranium and plutonium that do this, where a neutron hits them and they will then fission. And then you can do the whole chain reaction thing. They might well become the krypton and beryllium we had before. I think there are slightly other options. And if these neutrons, if one of them goes on to find another uranium-235, we'll have the chain reaction that we discussed at. So this neutron is making this thing fission. In the previous case, the last one we had, the particle, the uranium is just sat there and it just eventually randomly fissions. So what I've done with that. So this is induced. We are making it happen. Now, here's the equation for this. Uranium-235 plus 10. Now, if you add up here, you can see that the number of protons adds up. 235 plus 0 equals 56 plus 36. And along the top line, the number of neutrons also adds up. 236 and 90. Sorry, that's 3 lots of 1. So that's 92 onto 144. So, and that fits in with the idea of a chain reaction from Nat5. Now remember that if you went to the trouble of adding up the mass of all this and the mass of all that, now you often have to be careful that you don't forget the 3 because you'll only be given a 1 neutron value in the question. And that of course, this mass will be less than the mass you had at the start, and that mass difference we call a defect. And when you've worked out the mass defect, it goes into here. It'll be a small number. You times it by 9 times 10 to the power 16, and it becomes a bigger number. Okay, so I think that's a quick run through where we are with nuclear stuff. Task for you then, have a look at the course questions on page 15, 16, 17 and try and progress through. Do show complete working so that you can kind of indicate to me what kind of physics thinking you're coming up with. Okay. And do not hesitate to ask questions as you are going along.